And he thought, and I'm simplifying this a lot, he thought, those sound a lot like the same statement. I wonder if they're the same thing. So we're going to have, hopefully, a lot of fun today. We're going to talk about general relativity, but I want to try to keep it as simple as I can. That's why this is a pictorial introduction. Every slide that's in here is a picture, except maybe 10. So, like, I try to... out of, like, I don't know how many there are. There's a lot. Okay, but there's a few things where I got a bullet point, a couple of big ideas, and there's some text there, but most of it's pictures. So let's get right into it. We're going to have some fun pictures first. So let's take a look. So does anybody know what galaxy this is? I know we have a couple of physics students here.
Oh, is that two galaxies coming together, actually?
So this galaxy over here is thought to have recently interacted with this one, and that's actually might have distorted the spirals. So they are kind of a little close to each other. But this is the Whirlpool Galaxy. Its Messier designation is M51, if you're interested in that kind of cool astronomy stuff. It's a cool spiral galaxy in that we are from Earth, we're viewing like a top-down view on this galaxy. Whereas most other spiral galaxies, we get at a certain kind of tilt. So on the one hand, this is actually really terrible if you wanted to measure like how fast the stars are moving, because you can't get a beat on like redshift and stuff, but it's really cool to look at. So it ends up being really famous for those kinds of things. Anyway, does anybody know what this is?
That's just deep space Hubble, isn't it?
This is the Hubble Ultra Deep Field. Now, the Hubble Ultra Deep Field is one of the most curious things I think that we have available to us today. So what they did with the Hubble telescope, and I used to think it was a really strange amount of time that they had it stare at this thing, but I'll explain that in a minute. They had the Hubble telescope. They looked for like one of the darkest regions in the sky, in the constellation of Sagittarius, where there's like nothing there that we could see with the naked eye. And it's like a 2.4 arc-minute square that they looked at it. So this is not even a very large portion of the sky. It's very small, very, very dark. They pointed the Hubble telescope at it for 1,000,000 seconds. That's the number, which comes out to about 11 and a half days. Okay? And they had it just absorb every possible like type of light that it could get out of it. And this is the picture that resulted. It's approximated 10,000 galaxies in that picture. Each of those stars there, those bright things, like I think 2 of them are stars because they're the only foreground objects, but everything else is a galaxy that's billions of light years away, typically. Okay? And what's neat about this is that it actually, because light takes a long time to get to us, when you look far out in the universe, you actually also look far back in time. So if it's 1 billion light years away, you're looking 1 billion years in the past. Okay? So this actually, the further the object, the less structured it becomes. And they do this all the way back to like the cosmic microwave background and all this kind of stuff. Yeah, Bob?
Why is the sky dark?
Why is the sky dark? There's so much light everywhere. Right? This stuff is like remarkably faint. Like some of these here I think are like 1/82nd of the amount of light that your eyes can register or something, like the minimum amount of light or something. It's ridiculously below the human perceptible range. This is a very dark spot from...
That means it's not in the direction of the Milky Way.
Right, yeah. So like they specifically picked a location that had like as few foreground objects as they could obtain in order to make as dark of a picture. Because the idea was that they wanted to have like, they liken it to sort of like an ice core, right? Where you like drill down and you can see the history of the Earth because the ice kind of preserves what the atmosphere was like years and years and years ago. This is like an ice core drill of the whole universe. Right? So they stare back in time, you see what the universe was like, and sure enough, it gets less structured the older it is. The further back it is, the galaxies are less well formed and things like that, which supports some of the thoughts about the fact that the galaxy is constantly getting more and more complex as more and more structured, ordered as we go forward in time. But anyways, that's a really cool one. This is an artist's rendition. It's not a real black hole. This is an artist's rendition of what a black hole would look like with stuff around it. We actually have real observations of black holes now that maybe aren't still quite as cool looking, but, this is an old slide, so I didn't really change it, but yeah, black holes are pretty cool objects. We'll talk about those a little bit later. These are all sort of wonders of the universe. Go ahead, Joe.
Okay, so I see those rings of light sort of around it.
Yeah.
Are those, which one is supposed to be the event horizon, right around?
So the event horizon is the actual black part of the sphere. Okay, because nothing can escape the event horizon, including light. That's why it's black within it. Everything else is high. The closer you get, the more distorted it is. Like I think these two objects are actually the same object. It's just behind it, and so it gets distorted around it, and you see duplications of it. That's the idea of gravitational lensing and stuff like that. So they can actually measure the size of the foreground object by how it bends the light around it, and that's how they get the masses of most of these. That, and I guess they use orbital data, like how fast things are orbiting it and stuff like that, in order to get the mass of the object. So, bunch of different tools. Ask Joe Jensen or any other astronomer that we have here if you want to know more about how they measure all these cool things in astronomy, because that's not my expertise. This is an example. I actually deleted the Big Bang part of this because we'll talk about that later. But this is a picture of the expansion of the universe. Okay, this is another cool wonder that we seem to be seeing, that the further away an object is, the faster it's moving away from us, especially if it's outside of our local group. Inside of our local group, the gravity from the different galaxies are attracting each other and doing more interesting things, like Andromeda is like on a crash course for us. Triangulum's caught in our sort of gravitational pull. But you go far enough out to other galaxy clusters and they get further. The further you go, the faster they're moving away from us. Okay? That's an interesting observation that Hubble made, actually. And all of these are all large-scale structures in the universe. And there are a lot of things at play here, but one of the biggest, if not the biggest, determiner of large-scale structure in the universe is gravity. And that's what we're going to talk about today, is Einstein's theory of gravity. And a lot of the behaviors that we just observed can be described with this 5-character equation, which is called the Einstein Equation, Einstein field equation. It's kind of a little bit of a cheat to say that it's 5 characters, because those characters are defined to mean a lot of stuff. The G and the T are highly complicated. The 8 pi, or 4 tau, 4 tau, if you want. The 8 pi, of course, is there. In fact, a lot of mathematicians, they'll when they study this in mathematical relativity, they say, the constant doesn't really matter, just absorb it in the T. And they'll study the equation G equals T, which is a fun way of phrasing it, I guess. But anyway, it's interesting. All right, so we're going to take a little journey to see if we can understand where this comes from. So, I was going to ask if anybody knew who this was, but I realized I just put it in the title. Okay, so this is Sir Isaac Newton. Okay, this is Sir Isaac Newton. He is the father, we think of him as being the father of gravity, but he's also, what? Does anybody else know what he's really famous for, students? He's an inventor of something really, really important. He's the inventor of calculus, yeah. So,
Okay, never mind.
it's not the iPhone. Wrong Isaac Newton. No, so Isaac Newton independently invented calculus along with Leibniz, but he started formulating ideas about gravity based on what other people had done. So there's a lot here that I could go into, but to make sort of a long story sort of encapsulated, one of the things he did is he was trying to describe sort of what Kepler had observed that happened with planets and how they orbited. Kepler had several laws that were observations, like orbits are ellipses, and they pass out equal area in equal time, and a few other things like that. If you want to look it up, there's one about some complicated equation of what the period is at a certain distance or whatever. These were all observations that he'd made, but there wasn't a law that showed that they would work. So Einstein was looking for a way to write down what happened with gravity, and he came up with his law of gravitation, the G equals mm r, over r squared, right? G, all that equation, right? And that actually implies Kepler's laws. So his law of gravitation can be used to mathematically prove that Kepler's laws should work in a two-body problem. Okay, so that's a pretty cool thing. So, but in his viewpoint, what I want to talk about is sort of what view he had on gravity. Now, it was really successful for a really, really long time. But the viewpoint that he had with gravity, and I've heard different reports that even he didn't necessarily like the way that this was phrased. I don't know if that's true or not. I've just heard it from somebody. But that the idea, though, is that two objects pull on each other because of some invisible tether of some sort, some invisible force that's attracting these two bodies that you can't see, touch, but you can feel because it's pulling you towards the other thing, right? And you can measure it via, you can measure it via gravity. You can measure it in these kind of like as if it's an acceleration or a force, okay? And that's why he thought that it was a force. I'm not sure how much he liked the idea that there was this invisible force that you couldn't really see what was causing it, but that's how it was. And there's a couple of other assumptions that he made too. One of them was that space and time are two different things. Now, he didn't make these assumptions just because he wanted to make them. This is just what people thought of at the time. Nobody really thought space and time could be the same thing. They figured time was completely independent. Everybody measured it the same. Space was completely independent. And everybody measured distances the same. And so like so this is one of those bullets. That's not a picture. I told you about that, right? Okay, so here we've got here that the universal notion of how far apart different events were, everybody would measure the same. Right? So if your car goes from here to there in some amount of time, everybody would measure that length of time the same. And then also that distances in space were also measured the same via the Pythagorean Theorem, the three-dimensional one. Okay? If you want in polar coordinates, it looks like that. That's physics polar coordinates. So the theta is the 0 to pi 1 and phi is the 0 to 2 pi 1. Anyway, okay. But yeah, that's what it looks like in the Pythagorean Theorem for polar coordinates. Okay? And the thought was everybody measures those the same. And this worked out really, really well for a while. In fact, another thing that he also was comfortable with is, I'm going to define this as a world line. I don't think he used that term. I think that's a much later term, but it's the same idea. A world line is essentially the lifetime path of a particle. So from, if you want, you can think of yourself as a particle. From the moment you're born until you die, you follow a curve through the universe where your position, x, y, z, at any given time, t, is just a curve that's just parameterized. So we can just kind of follow you around, which, sounded really creepy before Facebook. Now it's normal. But we can just follow you around throughout your entire lifetime. And that's what we call your world line, whatever the graph of that is. And so from Newton's point of view, you could have no restriction. There's no restriction on what type of world line you have. Now, I want you to keep in mind here that in this sense, I've kind of merged all the three dimensions of space into a single line here, right? So to make a two-dimensional picture. But space is horizontal, time is vertical in this picture. So the x over y slope here would be your speed, right? So you can see that the more steeper it is this way, the faster you're going. Does that make sense? So the more horizontal, the faster you're moving. So this person's not moving very fast here, and then is moving really quick, that way in space, and then back up. You notice I have the time going forward because they all thought that the path, you should never repeat on the time axis or whatever. So you keep going through time, right? So if you want it, so a function of time. So any curve that can be parameterized by time would be a fair world line. By the way, just for later, since I'm going to mention this, a point in a space-time like this is usually called an event because it's a location and a time, which is what you give when you have an invitation to an event, right? It's giving coordinates of when to get there and where to go. Okay? That's an event. All right, so this was really successful. One of the other things that it said here, like I said, any curve is appropriate. So there's no speed limit, no problem. You can go as fast as you want. You just have to keep accelerating. But it turns out there are some problems. And even though it had some immense successes, and if you want to learn a little bit more about some of those successes, I gave a similar talk at the Roots of Knowledge a year or two ago. If you want to take a look at that, I talk a little bit more in detail about the history of some of this stuff, and I mentioned some more about the successes of Newtonian gravity. Some of them are pretty amazing, especially if you want to find out, if you want a cool story, find out how we discovered Neptune. It's pretty awesome. But anyway, I want to talk about the problems with Newtonian gravity so we can get into some of these other cooler pictures, right? One of the problems that was first noticed about in the mid-1800s, a guy, an astronomer named Leverrier, took a look at some data that had been collected over the last 150 years, measuring transits of Mercury around the sun. So what this is Mercury will pass through the sun and it'll drag like a little shadow across it, and you can measure how fast that shadow crosses across the sun if you have an appropriate measuring telescope that can see it. And so measurements had been done of this Mercury passing by, and they could measure how fast it was moving in front of the sun. And one of the predictions of Newtonian relativity and Newtonian gravity is that if there are other close by objects like Venus and Earth, they will tug on the planet Mercury per se, or any other planet they're near, And instead of having what Kepler saw in a two-body problem where you just have an elliptical orbit that stays closed and stays the same forever, in a multi-body problem where you have multiple planets that are close enough by to tug on it, it'll actually cause the ellipse to rotate a little bit, depending on how the forces are that are moving around. And you can predict this precession. It's a complicated computation that Skylar probably knows more about than I do. But you can calculate what the precession should be given the size of Venus and Earth and how it tugs on Mercury. And so they expected the perihelion, which is the closest point that Mercury makes to the Sun, would advance a little bit every year, or every several years, it's probably in order to measure it. And you can measure that by looking at where it passes the fastest, because that's going to be where it's closest. And so they can identify where the perihelion is and how far it moves across the Sun and get an idea of how much it's precessing. So Leverrier took all this data from all these precession calculations, or all these transit calculations, and he found out that the observed amount of precession over the last 150 years was a lot bigger than what was calculated and predicted by Newtonian mechanics. It was off by about 43 arcseconds per century, which sounds like maybe a little bit, but it was enough that it was statistically significant, if you want to. It was significant anyway. It's some reasonable percentage of how far off it was. So it was a good amount of error that made them realize something else is up there. And in fact, things like this is what led to the discovery of Neptune. When you see things not moving the way that they should up there, you can say, oh, well, maybe there's something else that's causing it, and they backsolved and they found Neptune. They thought about that here, but the difference in this problem is that everything that could be affecting Mercury would be inside our orbit to the Sun, and so we probably would have seen it. And so they couldn't find an extra planet that they missed that was causing anything like this. So it was just an open problem. Nobody knew why it was so far off. This was about 1859. Just left open. Nobody knew. Another problem about 18 years later, 13 years later, was the Michelson-Morley experiment. They were looking to try to measure ether drag, or how much passing through the ether, which is the medium that was supposed to permeate all of space, would affect the speed of light. And they set up a computation or experiment to calculate the speed of light in a bunch of different reference frames that should be going into the ether wind or going out of it at different various points. And what they found out was kind of surprising. I'm not sure how much they expected it or not, but they found out that no matter which reference frame they were in, the speed of light was always measured the same. And even if the ether wasn't there, you should have measured something different in each of those things because, for example, if you have a cop driving this way at 50 miles an hour, I guess the cop would be in the blue car, I don't know. But driving one way at 50 miles an hour and you're going the other way at 50 miles an hour, he shines his radar gun on you, what's it going to read? 100 miles an hour, and he's going to pull you over unless he's smart enough to realize that he needs to subtract off his speed too, right? Okay, so that's how Newtonian relativity should work, and it works just fine for slower speeds, like speed of a car or something like that. What's happening here is that if you had a rocket just careening towards a star at, say, 100,000 miles a second, and it measures how fast the light's coming off of that star, and then you do it traveling away from the star at the same speed, both of those reference frames will measure the light coming from the star at 186,000 miles a second. It doesn't matter that they're traveling in complete opposite directions at a relative difference of 200,000 miles a second. They'll still measure the light at the same speed, which is weird. It's not at all what Newton predicted, and nobody knew how to resolve this issue. Okay, so enter one of the most brilliant men who's ever lived, Albert Einstein. Now, again, like with the Newton thing, I'm going to leave out a little bit of the history here because there are a lot of people that influenced Einstein before he got to the point where he could start solving these problems. And so again, I'll reference, if you want to go check out that Roots of Knowledge talk, I spend a little more time on that than just talking about the general relativity. But I wanted to get more into math here. So Albert Einstein, he does some remarkable stuff at a very young age. A lot of the things that he proved that he's famous for, he did in his first year after getting a PhD. Some of which actually was while he was a PhD student. So, chew on that for a minute, in terms of what he was able to accomplish. But yeah, Albert Einstein, and actually he was also influenced very early on by one of his math professors, Hermann Minkowski, and he discovered, they looked at this thing called special relativity. So Einstein figured it out first, obviously, and he gave a whole bunch of talks on this. He'd come up with a way to resolve one of the problems that was really famous then. He resolved the issue of the speed of light being constant. He figured out a way to make that work. But the problem was that the model he had also didn't allow for gravity, didn't allow for massive objects. It was just inertial reference frames with no mass. So it's clearly not a complete theory, but it had enough to explain why the speed of light could be constant. And so he has a lot of computations that are based on like hyperbolic trig functions and a whole bunch of other kinds of things that you can calculate to do all of his things. But one of the important things that Minkowski kind of contributed to this is he said, there's actually a little bit more. Well, let me get through this part first. This is Einstein still. Einstein said Newton's wrong about one thing. Everybody should view space and time as being two sides of the same coin. Okay? So they're not separate objects that everybody measures the same. They're the same type of object. They're just different dimensions of the same four-dimensional space that we live in. Okay? They're not separated. And the quantities of the change in time and spatial distance could be measured potentially differently depending on where you're situated in the universe, right? So how you're observing it, you may observe certain things occur differently than another person will, because you're seeing the measurements of time and space separately, differently, but there's a unifying measure, and this is the part that Minkowski added, is that he told, after hearing one of Einstein's talks about this, he talked to him about it later, and he said, essentially, all of the stuff you just described can actually be modeled by a really simple Pythagorean theorem, absolute significant property, a value that everybody measures the same, this infinitesimal Pythagorean theorem that everybody's going to measure the same. It's actually a space-time distance quantity. Okay? So let's take a look at what I mean by this. Okay? So back to some pictures here. Okay, so here I've got a t equals t naught and an infinitesimally change in time to t equals t naught plus dt. I have a point at x naught, the point right above it, and the point that's a little bit over there. So if I can tell you how to compute the distance between this guy and that point over there, I've kind of told you what I mean by an infinitesimal Pythagorean theorem. Now I'm using that word, some of you that have taken Calc 2 or a physics class might refer to this as a line element or an arc length quantity. This is the thing that you integrate in order to get the length of a curvy curve. It's some kind of thing that we're going to talk about here. Okay? But this is what it looked like for this particular geometry that would produce the effects that Einstein was describing. And what it is it looks like this. It's pretty much the regular Pythagorean theorem, only it throws a negative sign in the t squared location. If you're a physicist, they flip the sign. Sometimes they also put a c in front of the t, a c squared in front of the t. That's to account for the speed of light. Okay? Does anybody know what the speed of light is?
290,792,458.
That's an impressive number of digits. I was going for like 3 times 10 to the 8th meters. Okay, that's the exact amount. Right, very good. Okay. What is the speed of light if I measure it in light years per year? 1, right? So why deal with these humongous numbers if I can just change my units to make it nice and convenient? So I'll measure all of my distances in light years and all of my time in years or light seconds and seconds, whatever you want. And the speed of light's suddenly 1, and I don't have to worry about it anymore. And so this is the equation if you use those kind of units, okay? Is it looks like that. And the geometry that this produces describes precisely what Einstein was talking about in special relativity. This is what it looks like in polar coordinates. So let's talk a little bit about what I mean. So I've talked about it a little bit like geometrized units, the idea of setting c equal to 1. But I also want to talk about the idea of induced inner product or dot product. How many of you know what the dot product is? I'm assuming kind of Calc 2 knowledge. Okay, dot product. That's the, if you have, sort of 2 vectors here, with like an x1, x2, x3, and you dot it with another vector, y1, y2, and y3, you multiply similar components and add them together like this. That is the dot product in R3. Okay, it's just a quantity. At first glance, if you just see that, you might not think it's really useful, but it actually turns out to tell you like pretty much everything about the geometry of R3, which is pretty cool. What I mean by that is most geometric statements that you can make about the geometry in R3 can be stated in terms of the inner product, the dot product here. I'm saying inner product because the generalization of the dot product is something we call in linear algebra called an inner product. Okay? But this is basically a dot product, and that line element, or any other line element, induces a dot product, if you want, locally, at least, in coordinates. In this case, for Minkowski space, it actually induces it globally. But this is what the dot product would look like in the Minkowski space-time. So you can see I take the time components and multiply them together with the negative. I take the x and the y and the z components, multiply them together with positives. If you're a physicist, you can flip the signs, whatever you want. That sounds terrible, but you know what I mean. Like, you just change the positives to negatives. It's not like flipping the sign on when you're driving down the road. That's not what I meant. Okay, but anyway, so yeah. So this is the dot product that you get. Now, this is interesting because now that we have a dot product on vectors, something curious happens here. Because most dot products like this one, if I ever dot a vector with itself, all of these quantities are perfect squares, right? Which means they're always going to be positive. So in the standard dot product, if I dot a vector with itself, I always get a non-negative number, and the only way I can get 0 is if the vector itself is 0. Well, as soon as you introduce a negative sign, you don't have that property anymore. Okay? So you can have quantities here, if they have a very large t value and small x, y, z values, this guy could dominate, and you could get a vector dot itself giving you a negative number. You could get a vector if the x, y, and z are bigger than the t. You could get a vector that is multiplies by dot products with itself to give you something positive. And if you have just the right amount of t and x, y, z together, you could even potentially have vectors that when they dot product with themselves give you 0. Okay? Which is a very curious kind of observation that you can have that's very different than the standard dot product in R3. Now, I already mentioned this. This is the idea of the c equals 1 thing. So what happens with this is that it gives you 3 types of vectors that you can produce. Vectors that dot product with themselves to produce a negative number are pointing more in time than they are in space because the time is dominating. We call that type of vector a time-like vector because it's pointing like time. If it's pointing more in space than it is in time, when you do the dot product, you get a positive number because the spatial components are bigger. Okay? We call that type of vector a space-like vector. A vector that has essentially the same amount of time and space, now keep in mind, again, c equals 1 in this context, would be pointing in a way that the dot product with itself would be 0. You can call those either null vectors or, as we'll find out, light-like vectors, because light travels along such vectors. Okay? Which makes sense because we set it up so that you think of it as just if you had like a t and an x, right? Like 1 and 1 or whatever, where you're moving just as much in time as you are in space. That means that you're moving at what speed? 1 time unit per 1 space unit, but we're measuring everything in years, so that would be like 1 light year per year. You're moving at the speed of light. So the only way you're getting that is if you're traveling at the speed of light, and that's why we call it a light-like vector. Okay, so this is interesting here because if we also operate under the assumption that we can, well, I don't know if it's really an assumption. What we observe is that we only move in time-like directions. Okay? We move faster through time than we do through space. How do we know? Well, because we're moving slower than the speed of light all the time. And there's no mechanism to move you from a time-like direction into a space-like one. So there is this kind of upper limit of how fast you can go. And there's other equations that can support this. I'm being a little hand-wavy because I want to get through sort of the pictures. But, I mean, for example, it would take like an infinite amount of energy to try to accelerate to the speed of light, that kind of stuff. I mean, there's a lot of weird things that happen with this. But the idea is that we're stuck inside of this light cone, only able to move in time-like directions, forward time-like directions. That's all we can move in. Which means that the only things that we can affect in front of us are the things that are in our forward light cone, because that's the only way we can send signals, is at speeds slower than the speed of light. So everything in that forward light cone, which is really a 3-dimensional like sphere traveling at the speed of light outside of us, that's the maximum amount of stuff that we can affect in the future. And the things that are behind us are that same set of spheres collapsing in on us, at the speed of light from the past. Okay? Those are the only kinds of signals that can affect us coming in. That's your past light cone. You can talk about causality and all sorts of stuff with this kind of thing. But this is an interesting thing that just comes right from the fact that you have this funky dot product that has a negative in the slot. And so now world lines are slightly different than what Newton did. They still have to move forward in time, just like Newton's did, only now they're never allowed to have a tangent vector that's not time-like. So the tangent vector along the entire world line has to remain time-like. That's what a world line is. Does that make sense? Okay? And you can compute the arc length of this by integrating over the length of the tangent vector at any point or whatever using that arc length thing. But you have to do you do it over the length of the tangent vector only since the length is going to be negative because the dot product with itself is negative. You have to absolute value it before you square root it and whatever. It's the same arc length formula from Calc 2. You just put an absolute value on the inside. And it produces, you can measure a length. And if you do, what's interesting about this is that the length is actually measuring more in time than it is in space. That length is measuring how much time elapses for you. It's a time measurement. So the length of your world line is how much time you experience. It's called your proper time. Okay? That's what this is here. So the space-time length of a time-like curve is called its proper time, or the time that the traveler along that curve experiences. Okay, yeah, go ahead, Patrick.
So intuitively, that cone is going to shrink when you move away from the essence.
So what's interesting is that when I'm at this point, the cone that I have here is exactly what it is. If I move, though, to this point, I now think of that as the origin and redraw the cone. So the cone actually moves with you in some sense and changes what you can influence. Because depending on what you choose to do, what your future allowable influence will change. Yeah, so the cone moves along with you. Interesting question. Okay. Well, as I said, this produces a speed limit. No one mentioned the fact that the last speed limit sign had a 19 on it, which is a very bizarre speed limit. I thought that was weird until I went to Disneyland and it's like 14.5 or something in the parking lot. It's weird. It's like, okay, sure. But anyway, the speed limit in the universe is the speed of light, specifically the speed of light in a vacuum. And weird things happen. So I want to take a few minutes here to talk about some paradoxes that come up. The first one is probably a more famous one, and both of them kind of illustrate the same kind of idea. But the first one is the twin paradox. Okay? And this is where we start to see that how we measure time can be different depending on where we're at. So if you have two people born at the same time, they do it 1990 here or whatever, and one twin is immediately put into a rocket, launched into space at close to the speed of light. In this case, I think it's 80% of the speed of light for this calculation. And you travel out there for 25 years from his perspective, so, and then turn around and come back, and then have that baby immediately turn back and come back around. By the time he gets back, the baby that was left on Earth will be 50 years old, but the baby that was in the spaceship will only be 30, which is kind of an interesting thing. And it's actually not hard to compute. So let's take a look at that computation for a second. Okay, so if we draw sort of Earth's world line, and let's just say, I'm going to turn the lights up so that I can catch, you guys can see this a little better. If I draw, say, the Earth's world line, and think of that as the place where the first twin's going to be, they're not moving in space from their point of view. We'll draw everything sort of from that point of view. Okay? So it moves from this sort of origin location where they launch the rocket and lives for 50 years until they come back. So its entire path is just along that. The baby, on the other hand, travels out, the other baby in the spaceship, travels out at 80% of the speed of light. And I didn't draw this very horizontal. If this is space and time, it's 80%, which would be 4/5 of the speed of light, but it's 5 in the time direction, 4 in the x direction. So it's actually like a 5/4 slope from this perspective. Something like this, and then immediately turns around and goes back. And this location here, from his coordinates, is at t equals 25. So if you want, we can actually start identifying coordinates on here. So you get 0, 0 for the origin. Up here, this is, let's do time first and then x, because that's how our dot product is. So this is going to hurt your head if you've taken calculus, because we always do horizontal first, but I'm going to do vertical first. Okay? So tx, that's how I'm ordering the coordinates. Okay? Up here, this is 50, 0. Okay? This guy travels at 80% of the speed of light for 25 years. How far does he go? How many light years? 20. Those 20 light years, okay? And we're measuring everything in years, right? So the coordinate of this point is going to be what then? From his point of view, it's going to be 25, 20. Okay, so this is the coordinate from his point of view of that location. All right, so this guy goes to this point and then goes up there. Now let's measure what they experience. Now you have to measure everything from this guy because he's the only one that's actually in an inertial reference frame. This actually shifts into two different inertial reference frames when he suddenly turns around, which would probably kill the baby, but we want to keep happy and all that. But whatever. Okay, so let's measure the lengths here of how much time's elapsed. So the length of time, the length of this curve here, according to the Pythagorean Theorem that we just wrote down, which most of the time on other kinds of spaces like this, you'd have to integrate. But this is actually a global metric. Like you can measure this however, with coordinates like you do in R3, and doesn't have to worry about being infinitesimal because it works really nice. But so this one here, we can measure that distance there as ds squared. So we want this guy, this distance here, will be equal to negative the change in time squared plus the change in x squared. And I only need to do 2 dimensions worth because I've suppressed all the other 3. Okay, that's the length that I'm going to do. ds is the value I want. dt squared, what's dt? That's how much difference I have in time. So that would be 50 minus 0. 50 minus 0 squared plus the distance in space, which is just 0 minus 0. I get negative 50 squared is ds squared. Now keep in mind, when we are actually computing the length, we have to square root an absolute value because we want to get a positive value out. This, by the way, is why physicists flipped the sign convention. Because if everything's a time-like curve, they don't want to have to worry about having an absolute value all the time. So they might be a little right on this, but don't quote me on that, even though I'm recording myself. But anyway, okay, yeah. They flipped the convention to make it work nice for these kinds of things, okay? But anyway, this tells us that the length is actually going to be the square root of the absolute value of negative 50 squared, which is, of course, what? 50. Okay, so he measures 50 years, which is exactly what we expected, right? That he should experience 50 years of time. Okay, now let's do the same computation for these 2 legs, okay? Now, can everybody agree that it's symmetrical? So whatever length this is, that one's going to be the same, so we just compute this one and double it, okay? So let's do that. So ds squared for this guy is going to be negative dt squared plus dx squared again. Now, put in the distance and time, change in time coordinate he had, which is 25 minus 0 squared, plus 20 minus 0 squared. That's the distance in x, right? Okay. And what do you get here? You get negative 625 plus 400. Did I do my math right? I hope. Because otherwise it's really embarrassing because I'm in front of a bunch of mathematicians, but that's okay. Right? I hope that's right. So this comes out to negative 225, which when I square root, I get a ds. I do the square root and absolute value of negative 225. And what does that come out? What's the square root of 225? 15. So the length of time this guy experiences during that journey is 15 years. Double it, 30 years. Boom. Experiences less time. That's weird. Okay? But that's how you resolve the twin paradox. It's just an artifact of the geometry produced by this inner product. Okay, want an even wonkier one? It's a Toyota Corolla. No. An even wonkier one. I couldn't find a good picture of this. Oh, go ahead, Bob, before I get into this.
Is that dependent on acceleration that they get back?
So there is a little bit of...
To get back to where they start, it requires acceleration, and you can get the same thing with actually some gravitational effect.
Right. So if you want to, so this model that I drew. So Bob's asking if they're like what's the real physical situation here. The model I drew is a little simplifying. This suddenly shifts from traveling 0.8 the speed of light that way to suddenly turning around and going 0.8 the speed of light the other way, like instantly. It's got a complete discrete change, from that. It's not very continuous. Definitely not physical, especially for the baby. I don't know, maybe he felt it was physical because he probably splattered again. Okay, it's getting dark. Okay, anyway, yes, if you wanted to make it physical, you would have to accelerate around here, which would actually move it outside of the realm of special relativity. So you would have to take into account a general relativistic effect. But if you do it, it still comes out to basically the same thing.
Yeah, the calculation is the same, but if you just have inertial things, you don't get that kind of time. It's a different phenomenon. But they did test this by the acceleration of atomic clocks on rockets.
Right. Yeah, you can't, and I'll actually talk about it a little bit later. You can't suddenly shift inertial reference frames like this, like suddenly. But if you do it just as a sort of simple thing, this is the computation. That's where it comes out from. So this one's a little. Oh, go ahead.
I'd like to quickly point out that at the point the child turns around, 15 years have elapsed for him, and it's no longer a baby but a teenager, and therefore less sad.
Fair enough. So, less disturbing if a 15-year-old splats against. Okay, stop. Okay, all right. Okay. All right. Okay. Wow. All right. So, yes.
So I understand this calculation, but why along the distance along this line here, why does it mean how old he is becoming?
So this is a measurement of space-time length that he's moving. And since he's moving in a time-like direction, that's kind of why it goes. They're trying to match a model to what they're observing. And so that's why this kind of ends up.
You actually would observe.
Yes, that's what it was, and we've observed this experimentally. I'll show sort of why.
And of course not with people becoming older, but the atomic clocks and all.
Right. So it's important to point out too, this is not how Einstein first envisioned the twin paradox. He did it with a bunch of other kinds of math like hyperbolic sines and cosines or whatever. But this is what it would look like if so Minkowski was trying to model it with a geometric thing. So this geometric model with that kind of assignment is what modeled what Einstein was talking about. And so that's kind of where this is coming from. But the idea is that actually showing reality? And it does, in fact, because we're actually able to experimentally verify this now. So, and I'll get to in fact, you experimentally verify it every single day, but we'll get to that, why you do. It's actually really cool. But, okay, I'm going to interrupt myself here. I didn't do a very good job of answering that question. The question is why is the length of your curve that you're traveling in, your world line, why is the length of that your proper time? And there's actually a really good explanation for this that I didn't do a very good job in the talk giving. So the reason why it is the following. So I'm going to draw a little bit of a picture here. If you were just standing still, this would be your world line. The only thing that you would perceive that you experience is your motion through time. And so how do you perceive that? Well, you would perceive that as you move along this curve here. And so your perception of your motion would only be through time, and how you measure that time out, like how you measure out your tick marks on it, is what your watch reads. So your length here along this curve, or along this path right here, would be your time. Now, what if another person is traveling at a certain rate of speed away from you at that time? Well, they're going along this path. The thing is, that's an inertial reference frame from their perspective. So from their perspective, they're actually not moving, you are. So this path that they're traveling, to them, feels like they're stationary, and the only thing that they're experiencing is time. So how they would tick out their mark is just how their watch moves along that path. And that's why they would think that their motion is completely just time, because they don't see themselves as moving, and their space-time length is just the time that they experience. But from our perspective and their perspective, we have to measure the lengths of these curves exactly the same. And so using that Minkowski metric is what allows us to measure the lengths of these curves. He would measure our length the same way as we would measure the length there, the space-time length. And sure enough, we measure this one as having experienced less time than the one over here during the same period. And so that's why you measure your proper time is simply the length of the world line you're on, because from your perspective, you're always stationary. So the only motion you experience is time. So how you would tick out your time as you move along is how you measure the length of your world line. And that's why it ends up being your proper time. So now we'll join me back in the talk. Let's talk about an even weirder paradox, okay? This is the car and garage paradox. Some people use a ladder, but a car is more fun, because I don't want to run a ladder at most of the speed of light, okay? But so there's another phenomenon that's predicted from Einstein special relativity, which is the idea of length contraction, okay? This kind of looked at time dilation, okay? The amount of time that passes. If this guy at this speed was to travel for 50 years, he would travel further, and he would spend more time of this guy's coordinates from his perspective than 50 years, right? From his perspective, more than 50 years would have passed, and that guy would have experienced 50 years. That's the time dilation effect, because he's experiencing more time, the guy at rest, than the person moving. There's also a corresponding length contraction effect, which says that if you're observing a very fast-moving body, the measurement of how long it is shrinks a certain amount, okay, from what its actual rest length is. So the thought experiment here is, I have a car that is, and I've seen some really cool cartoons up here that I wish I could have added that had Batman and Alfred with it in a garage. But anyway, I have a car that's exactly the length of a garage. So if it's sitting in the garage, its front bumper is touching the back of the garage, the back bumper is touching the front door. It is 100% in there, exactly same length. That's what it is at rest. Now, I'm going to take that car and travel 88 miles an hour to travel. No, it's going to travel a lot faster than that, okay? I'm going to take this car, it's going to travel at a very large fraction of the speed of light, say 0.8, whatever you want. You can actually do these calculations, but it's kind of more fun just to see the geometry of it. So we've got this car that's traveling at a massive amount of speed, close to the speed of light. And we have the guy driving the car as one observer, and we have another guy standing in front of the garage as another observer. Now, as the guy standing in front of the garage observes the car traveling at close to the speed of light, the length of the car contracts, which means that the car is actually going to be shorter than the garage. So from his point of view, the back end of the car should enter the garage before the front end of the car crashes out the back. And we won't stop. We'll let it go ahead and crash out the back, okay? So he observes the back end of the car entering the garage before he observes the front end of the car crashing out the back, because the car is shorter. But from the other point of view of the guy in the car, from his point of view, he's stationary and the garage is moving. So the garage is traveling at close to the speed of light towards him, and its length contracts, meaning that from his point of view, the garage is shorter than his car, and he will observe the front end of his car crashing out the back before he observes the back end of his car entering the garage. Seems totally unfeasible. That's weird. Okay. It turns out it is completely beautifully described by this same geometry here. So, let's see if I can do this one. This one's a little trickier to draw. Okay, so we're going to draw a path here. This is from, this black coordinate system is from the point of view of the guy standing in front of the car. Standing in front of the garage, okay? And we're going to look at this point here as when the front end of the car passes the front part of the garage, okay? So at that point, both observers are about at the same location. So I'm going to assume that point is in both of their reference frames, okay? That's right when they pass each other. Okay, at some point, well, so first off, the guy driving, this is only the second time I've drawn this diagram today, so I'm hoping that I do it right. The guy driving the car is traveling at a significant fraction of the speed of light. So his actual path, or world line, is going to be a certain slope, and I should have brought my ruler so the image is going to be even worse. He's driving at a certain slope about like that, okay? This is his time watch, so that's actually his time coordinate line. Now, his coordinate system has to remain orthogonal, meaning just like the TX one here over here had to stay orthogonal, right? But what does orthogonal mean? Does anybody remember from Calc 2? It's not 90 degrees, it's something to do with the dot product. Orthogonal means dot product is, you're in my linear algebra class. What's orthogonal mean? The dot product 0. Okay, great. Okay, so that's what orthogonal means. But the dot product here, remember, is negative t squared plus x squared, essentially, or dt squared, dx squared, okay, right? So if I have a, if you want a 5/4 or 4/5 slope, 4/5 the speed of light guy here, then in order to have an orthogonal vector that's going to dot product that way to produce a 0, it has to be 4 time and 5 space. So it's actually producing something about, oops, I want to do it in green. It's producing something about like this. And this is where it gets weird. That's his x-coordinate. That means, so this here, this x-coordinate, this x-axis, is all the points that this guy in the black observation thinks happen at the same time. This x-coordinate are all the events that the car guy thinks happen at the same time. Does that make sense? So this x and x prime are their corresponding surfaces of simultaneity. Those are the events that they observe as occurring at the same time. Okay, so let's see what happens. This guy, this is where the front end of the car, I'll use F for front, hits the garage, the front of the garage. Okay? I'll use G for front of the garage. That's what happens here. And I know I'm kind of running low on time. I'm having too much fun with this. He goes out a little bit a ways, okay? This is where the front end of this is the event where the front end of the car hits the back of the garage. Okay? And notice it's along that t-axis because that's his world line. The front end of the car is what I'm measuring the driver off of. It's a really dangerous place to drive a car, but anyway. On the other hand, this guy here, we know that this path, he saw the car contract, so he should see the event of the back end of the car hitting entering the garage before he sees the front end occur. And so he's actually seeing the rear hit about, I want to make sure I do this in about the right distances. It's hard to do this without a ruler. Let's say it happens about right there. Okay? So this is the rear end of the car hitting the garage. Notice it's along that line because that's where the other observer is. So he sees the rear end of the garage hit there. Now, the question is, how do they compare and how they see these things? And so now we need to sort of see what's going on at that point. So after this guy has traveled along in time to see the rear of the car hit the garage, these are the events that he sees as being simultaneous. Okay, so this is the guy in front of the garage. He sees those events as being simultaneous. You can see that this event is in his future because it's above his x-axis. So he sees this event occur first and then this one. So the garage guy sees that event first and then sees this event second. Okay? On the other hand, this guy, when he measures his simultaneity, they're parallel to this line here, and this is why I've drawn this probably a little poorly. I needed a yardstick. So he sees the surface of simultaneity for that guy as being that. Okay, those are the events that he sees as occurring at the same time here. Notice that's parallel to this thing. That's his x-axis at that point when he's traveled along that far. It's still parallel to this one here, because remember the directions have to stay orthogonal to each other via this thing here. Okay, so it's all based off of orthogonality with this thing. This event here, if you want to see where he sees this one, you have to follow that same line. He sees it occur around that time. That's the point of time in which he sees this event occur. And so even without moving the points, from the car's perspective, he sees this one occur first, and then he sees this one occur second, because it's on different surfaces of simultaneity. So because the fact that how they see simultaneous event changes depending on how fast they're going, because their simultaneous events has to stay orthogonal to their path, they can actually change the order in which they see events occur without moving the events. Do you see that? Those events didn't move. That's just how they perceive them. So there actually is no paradox. It's just a wonky geometric picture. Okay? Really weird stuff. Okay? But it's interesting to see. I'm a little out of time, so let me kind of jump ahead a little bit here. I'm going to turn the lights down again. So the main ideas of general relativity, we just talked about sort of special relativity paradoxes. This is supposed to be a pictorial introduction to general relativity. So where did this go? As soon as Einstein recognized that what Hermann Minkowski was telling him was a good thing, he went and started learning everything he could about Riemannian geometry because he thought that could have the answer to what he was trying to do. Because remember, special relativity didn't describe gravity yet, and he was really struggling to find out how to fit gravity into the situation. But he realized that there's a couple of really cool observations that you can make. In a curved space, you have to keep track of what's called a curved derivative, covariant derivative or whatever, but think of it as a curved derivative. If you're on the surface of the Earth and you want to move a little bit, you want to move along, you want to measure what that path is going to be like, but you have to stay on the surface of the Earth, you have two things that sort of affect your path, which way you're trying to move, and then the fact that you have to stay on the surface of the Earth. Those are two things that affect your position. The part that the Earth is affecting by trying to keep you on the surface has to be accounted for when you're trying to figure out how fast you're going, because that kind of automatically happens. So what a curved derivative does is it takes into account how much your position is going to change due to not only the fact that you might be moving, but also the fact that you have the space going along. So this gives us an idea of how to think about a straight line on a curved surface. A straight line in calculus is a line that has 0 second derivative. Right? 0 second derivative, non-accelerating curve, is what a straight line is in calculus. Well, if you take a second curve derivative for a curve and have that set to 0, that is the straightest possible line that you can get on that curved surface. It is a non-accelerating curve in the sense of staying on that surface. So in other words, it's a curve whose motion is only controlled by the fact that it has to stay on the surface. So one way you could think of it, this path, which is called a geodesic, is a path whose motion is controlled by no other influence other than the surface of the space that he's in, other than the curvature of the space. So motion under no other influence other than curvature. Well, Einstein realized that free fall, if you just drop an object in a gravitational field, that's moving under no influence other than gravity. And he thought, and I'm simplifying this a lot, he thought, those sound a lot like the same statement. I wonder if they're the same thing. And so what he realized and was able to show mathematically was that massive bodies will curve space-time. I'll do it with this picture. Massive bodies will curve space-time, and objects will try to follow geodesics in that curved space-time. So the Earth orbits the sun not because there's some invisible force pulling it or attracting it to the sun, but because the sun itself warps space-time around it, changing the geometry of both space and time, bending them in funky ways, just like these weird paradoxes, okay, but even like more distorted. And the Earth is trying to follow a straight path in that wonky geometry. And so it gets stuck in it, and the best it can do is follow a geodesic, which in this case would be an orbit. And you can prove that the geodesics of the right space are in fact orbits. Okay? So this picture of curvature. But that's actually what this equation says. The Einstein equation, this G here is called the Einstein curvature tensor. It is a measure of the curvature in the space, overly simplistically, but it's a measure of the curvature in the space. This T here is called the stress energy tensor, and it's essentially a measure of like where the stuff is in the space and like how it moves and stuff. So this system of differential equations, actually, it's like 10 of them, 10 differential equations, all coupled together in sort of tensor stuff, essentially says that the curvature or the geometry of the space-time, is equal to where the matter is. So matter curves space-time. That's the simplest way you can describe what the Einstein equation says, is that matter curves space-time. Geodesics, like I said, are non-accelerating curves. Free fall is motion under no influence other than gravity. That's going to be geodesic. That's what he realized. And what does this do? Okay, so suddenly, real quick after he had this, you could see a lot of things occurring, and within just a few years after he figured this out. So special relativity was about 1905, 1906. General relativity was 1915, is when he figured this all out. By most of the results I'm going to show you were known before 1920, because that's how fast it started solving physics problems. So one of the ones that it did is you can find the space-time around a star, and this is where the person who's responsible for this is Carl Schwarzschild, who unfortunately died of the flu during World War I, I believe, and apparently did general relativity computations while he was fighting the war. But anyway, which is kind of cool, I guess. Really, really neat, actually. But he figured out that the Pythagorean Theorem around a star looked like this. I know it looks really, really complicated. Okay? Don't worry about the formula itself. But the fact that he could find the infinitesimal Pythagorean theorem around a technically non-rotating star gave a lot of insight, because now you had this, you could start doing computations like this and figure out things about the geometry. And it turns out that under this situation here, if you start computing out what the geodesics are, it turns out that the orbits it predict precess on their own. So not only will they be affected by other planets that are in there, but if you just had a two-body system, a star and a planet, that orbit would precess. It's called relativistic precession. And when you add that effect into what's going on with the Sun and Mercury, the amount of relativistic precession predicted by general relativity is exactly the missing amount from Leverrier's computation 40 years earlier. Isn't that nuts? Like, it was dead on. Well, almost dead on. I mean, nothing's really dead on in physics, but it was really, really close. Okay? So it totally describes sort of where this extra stuff was coming from, this extra observation. So solved the precession of Mercury problem. This was the point. Before this observation had been made and this computation done, people were kind of a little skeptical of what Einstein was trying to say. Because realize what Einstein was doing is he was revolutionizing. He was basically saying Newton's theory not so much was wrong, but was dramatically incomplete, and can only describe situations where speeds are really slow and masses aren't very high, which is basically the situation of when you're building a bridge and stuff like that, which is why we still use Newtonian mechanics to do engineering and stuff, and it's okay, bridges aren't going to fall. But you couldn't build it, as we're going to find, a GPS system using Newtonian gravity. It won't work, okay? And we'll see why. So one of the cool things about the Schwarzschild metric is in the appropriate limit, it actually recovers Newton's equation. So Newton's is actually like the linear approximation of this system, which is kind of cool. It also is the first mathematical way of predicting sort of a black hole-like object. I think black holes had been conjectured physically before this, but This was the first time I think we had a calculation that actually could predict something like this, and we later observed them. It also, so let's talk about GPS. This is another cool thing, and I'm getting really close to where I can stop. GPS systems are an amazing thing, and if you want to, you asked earlier, how do we know this, right? So have to experimentally verify it. GPS systems are exactly this. GPS satellites travel a lot faster than we do. In relation to us, they're traveling remarkably fast as they orbit the Earth. The speed at which they're traveling has a special relativistic effect like this, in which case we would expect to see their clock on the satellite run a little fast compared to ours. So, or the other way around, runs a little slow compared to ours. Ours would take longer, theirs would be short. No, it would run, yeah, anyway. The appropriate direction, I always get it mixed up. I think it runs a little slow. But there's another effect that's going on. The effect that the GPS satellite is further away from the center of the Earth means that it's further outside of the gravity well of the Earth. And so space-time is distorted less where it is than it is where we are, because we're closer to the center of the Earth. That causes our clocks to speed up by, comparison to theirs. One of them is a slowdown, one of them is a speed up. I can't remember which one it is. But the overall effect is that in order for the GPS satellite to remain synced with your clock in your car so that it can give you directions in real time, they have to artificially run the clocks on the satellite slow in order to stay synced with ours. So a second on the satellite will be longer than a second here because their actual seconds are faster. So does that make sense? So like how fast a second elapses on the satellite is faster than how fast the second would elapse here. So to make it synced, we have to make our second what his second is on the satellite. So we have to artificially elongate the thing. And I think the first thing I said about which way it was going was right, now that I think about it. Okay, anyway, whatever. Okay, but the idea is that they have to run the clock slow. Now they do this in a really remarkable way. They do it with atomic clocks because it isn't just a machine counting here. This can be observed in decay rates of particles. So an atomic clock measures how fast time has gone because a particle is decaying, and they know what the decay rate is. The decay rate of the particle on the satellite is faster than the decay rate here on the Earth, by comparison. So they use that as a calibration tool to find out what an appropriate actual second is on the satellite compared to an actual second here, and that allows them to calculate how much longer they need to make the second to make it match ours. And if they didn't do this, the GPS satellites would be like, it would go inaccurate like 10 kilometers a day. Like that's how far off it would be. It would be completely obsolete in a matter of hours, okay? Which is amazing, which means that like if they didn't know this general relativistic thing and tried to do a GPS system, it would just break like almost immediately. It'd be a humongous waste of money. But every time you get in a car and say, hey, Google, navigate me to Walmart, I hope you know where your Walmarts are, but whatever, okay, navigate me wherever you're going, okay, you are accessing technology that is based upon general relativity in order to give you directions in real time. And if they don't do it, it won't work. So that's a pretty cool everyday application and a verification that this model was correct, or at least in every possibility that you can. And I have a few other things. The Hubble Ultra Deep Field is kind of a neat thing, and I'm out of time, but the idea here is that everything looks the same basically no matter which way you look or where you are in the universe. Those two observations, which the Hubble Ultra Deep Field seems to support, produces a metric like this, okay? Overall, so this is like a cosmological scale. This is what the metric would look like. You see you have this scaling factor here that only depends on time, and it's multiplying some metric that could be flat, spherical, or whatever. But the interesting thing is the differential equations on this can be used to show that this function has a zero somewhere in the past. And if it has a zero somewhere in the past, that means all those spatial distances at some point in the past were at a single point. And Lemaitre, who was the first person, I think, to observe this, he coined this kind of jovially as a Big Bang. This was the moment when the sort of whole universe sort of exploded into existence. But if you look at this model, it's not like an explosion. It's like the moment after it happened, the universe was infinite, which we don't really know if it is or not. But that's what this model would predict. So if the model is correct, that's kind of what's going on with it. But that's where the idea of the Big Bang Theory comes from. And you can actually do this calculation for what it would be, this expansion, because you can find out what the appropriate rate of change is right now, because we can measure how fast things are moving away from us, which gives you an initial condition. So you can then use that initial condition in the differential equations to project back when the zero would be. And I did this calculation in grad school, but don't ask me to repeat it right now. I probably couldn't do it on the fly. But you can calculate it. Hubble, by the way, showed that the expansion was actually occurring. This was really wonky at first. People didn't really thought this was actually a big problem for general relativity because everybody thought the universe was static when he was around. But Hubble observed that it actually did expand. And so if you compute when this Big Bang would have occurred, and you can do this computation, it's about 13.75 billion years ago. And that's why we think the age of the universe is about 14 billion years. The assumptions that lead to that system of equations kind of break down when you get closer to where the Big Bang singularity would be. And that's why we have these extra things that they're talking about that may include things like, what's the right word? Can't think of it. It's sort of fast expansion. Inflation. Thank you. That's the word I'm thinking of. That's why they have these other predictions, because they have to go to quantum mechanics to try to figure out what's going on in the early days of the universe, because some of these computations don't quite apply when you get into that kind of high density stuff. But anyway, roughly about that. So really cool stuff. These guys, they're really cool. They won a Nobel Prize about 11 years ago, 11 years ago, for showing that the expansion of the universe is actually accelerating, which can be potentially modeled by introducing a cosmological constant, which is kind of cool. So you change the stuff out. Once upon a time, I studied stuff about dark matter and dark energy. This is the bullet cluster. It's actually really cool. The blue is dark matter. The pink is regular matter. You can kind of see it separating out, which is kind of a neat thing. There's some other stuff that's not really important. Anyway, the point is that there's possibility, and if you have some time, you can ask me about it another time about how this might relate to dark matter and stuff. I'm maybe about 6 or 7 years out of the game, so there's been a lot of research done since I probably did anything on this, so I'm probably a little out of date with some of it. But really cool stuff that you can see that maybe general relativity could maybe describe some of these other mysteries that we don't know. Anyway, hopefully that was fun. I'm sorry I talked really fast at the end there, but anyway, thanks for listening to me. One interesting observation that I saw Neil deGrasse Tyson make, which was really mind-blowing. So these things here, the space-time length that you travel on is your proper time, right? That's how much time you experience. But light particles, photons, travel along null curves or light curves, which if you compute the length of that curve, it's 0, because the dot product of that vector with itself is 0, which means that a photon experiences its entire existence in a single instant. So from where it's birthed in a star to any other point in its entire existence, to like when it reflects off the wall or your glasses in your eyeball, whatever, it experiences all of that as a single instant and has no clue. I mean, it had a brain, I suppose, but has no clue that there's anything other than the whole universe. And a photon would probably find the idea that we experience time as weird as we think of it not experiencing time, which is kind of weird. I don't know, weird stuff. I think it's fun. Hey guys, thanks for watching my video today on Philomath Party. If you enjoyed today's video, consider giving it a like, and consider maybe subscribing and hitting that notification bell for this channel. It'll help us know what kinds of videos you guys like so we make more of them. Anyway, I hope you enjoyed today's video, and we'll see you next time.